Nerve impulses. Let's talk about action potentials and synapses. So we're going to start here with what is called a resting potential. This is where you are creating a potential across the cell membrane. We're calling this an electrochemical gradient because it has an electric component and a chemical component. The sodium-potassium pump is going to put 3 sodium ions out. Each one of those ions has a positive charge. And it's going to allow 2 potassium ions in. Each one of those ions has a positive charge. This is a net export of 1 positive charge per movement of the sodium-potassium pump, which costs 1 ATP. Now there's a higher amount of potassium inside than outside, and it wants to go out down its chemical gradient. And potassium leak channels will allow potassium to leak back out down its chemical gradient. However, as more positive charge accumulates outside the cell, the potassium doesn't want to go against its electric gradient and doesn't want to go where there are more positives on the outside. Sodium leak channels will allow a very limited amount of sodium back in, resulting in a net positive charge outside and a negative charge inside for a negative 70 millivolts across the membrane. Here you can see it with a sodium-potassium pump pumping 3 sodium out and pumping 2 potassium in with a higher concentration of sodium on the outside and a higher concentration of potassium on the inside, a negative charge on the inside and a positive charge on the outside. Now that all can get changed by something called graded potentials and graded potentials called depolarizing and hyperpolarizing. Depolarizing makes this charge less negative. It's going to basically allow some positive charges in. Allowing positive charges in makes it less negative. So this is depolarizing. Hyperpolarizing is going to make charges more negative. So perhaps forcing more positive charges out is going to make it hyperpolarizing. Now, if 2 of these graded potentials occur in summation, where one occurs and before the resting potential can be resumed, another occurs, you get what is called summation, where you're adding together the 2 graded potentials. If you add a depolarizing and a hyperpolarizing, you can kind of get no real effect. But if you add 2 depolarizing, you may be able to reach something called threshold. Threshold is where you're going to create what's called an action potential. Now let's look at how that happens exactly. When you reach that threshold, this is going to open certain things called voltage-gated sodium channels. They're gated until a certain voltage is reached. That voltage is the threshold voltage. And when these open up, they allow the sodium to flood in. And when the sodium floods in, this is a lot of positive charges that are going to come in. There are also something known as voltage-gated potassium channels. If that voltage becomes net positive across the cell membrane, i.e. if a lot of sodium have been allowed in, these will open up and allow potassium to flood out, not just leak out. Both channels will shut after a certain amount of time, so they're not going to just open and stay open. They open, shut. The actions of these together is what creates an action potential. So let's say you reach threshold. What happens is there's going to be a rapid depolarization as the voltage-gated sodium channels are opened. When they're opened, the sodium is going to flood in. So you can see that sodium kind of flooding in, and as it does, you have a depolarization. When that depolarization reaches 0 and starts becoming positive, you open up the potassium channels. The voltage-gated potassium channels will open and allow potassium to flood out. So that you let a whole bunch of positives in, and then you let a whole bunch of positives out. So it goes up and it goes down. It becomes more positive, it becomes less positive. And there's this bit of an overlap there where they're kind of still shutting. Remember I said they'll open and then they'll shut, and they'll stay shut for a little while and cannot be reopened. So you can't just go up and down really fast. And there's a bit of an overshoot there as all the potassium's gone and all the sodium's also being pumped out again as you reestablish the resting potential using the sodium-potassium ATPase, which will reestablish that resting potential afterwards. And this is all occurring in a matter of milliseconds. So what will happen is this will actually self-propagate down an axon because allowing the sodium in is going to change the voltage. It's depolarizing. And as it depolarizes, it's going to reach threshold, and the next voltage-gated sodium channels in line are going to also open. So voltage-gated sodium channels allow more voltage-gated sodium channels to open, and this propagates down the membrane. Now, following that movement of a positive charge down the membrane is going to be the potassium channels opening and causing a negative charge across the membrane. And that means you're actually going to get this propagation of an action potential down a neuron from where the neuron starts to wherever it finishes. And there's something called the refractory period. Remember how I said those voltage-gated potassium channels and voltage-gated sodium channels are shut and cannot be reopened for a little while? That means that you can't make another action potential right after making an action potential. This also means that the propagation can't go down and then start going backwards. And that allows it to be unidirectional down the axon to the end of the axon. When it can actually make it faster by putting on something called Schwann cells or myelination. This is a fatty insulating layer around an axon, which makes the axons kind of white colored. There are these cells around the axon. If you see white matter in the brain, that is this myelination, making for faster transmission of an action potential. And you'll see a lot of nerves are white because they are myelinated. And it's actually a bundle of a lot of axons together. At the end of the axon, you may have a synapse. This is where a nerve meets another nerve. When that nerve reaches another nerve, you're going to have that action potential traveling down the axon to the synapse. As the action potential reaches the end of the synapse, you're going to get the voltage-gated calcium channels opening. And voltage-gated calcium channels opening allows a lot of calcium to come into the cell. When calcium comes into the cell, it triggers the fusion of vesicles that are full of neurotransmitters with the synaptic membrane. As these vesicles fuse with the neurotransmitters, they release the neurotransmitters into what is called the synaptic cleft, i.e. the space between two neurons. And the neurotransmitters will be released into the synaptic cleft, and then they will bind to a receptor on the other cell. And as they bind to a receptor on the other cell, they're going to cause some sort of ion to come in. Perhaps this is going to allow sodium ions in. If it does, this is going to cause a depolarizing graded potential. If it allows like chloride ions in, this is going to cause a hyperpolarizing action, a hyperpolarizing graded potential. So this is how those graded potential occurs when an action potential of one cell comes to another and causes this change at the synapse.